Hey everybody, let's talk about the physics of music. I think this is going to be kind of cool, which is, it's the end of the year. We got really just 1 week left. So I thought I'd just do some stuff that is interesting, at least to me. I hope you guys like music. Most people like music. Anyway, I love music, and it's a big interest of mine to talk about how we can analyze music scientifically or mathematically. And it is part of this unit. I mean, the waves and sound unit, music is part of it, kind of explaining how sound works from a physics perspective. So let's get into it. By the way, this is a presentation I made several years ago for math class. So I've sort of adapted it a little bit to be more of a physics lesson instead of a math lesson, but it's really both. So you can kind of approach it from both of those perspectives. Like think about the math that we're doing here, but also think about the physics that we're doing here. So this is a bit of review. I already kind of talked about this, but sound travels as alternating layers of denser and less dense air particles. Um, oops. So here's a really good graphic of it. This is similar to what we looked at last week, but these denser bands of air particles are like the crests of the waves, and then the spaces in between, which are the regions that are less dense have fewer air particles in them, as you can see from where my mouse is following. Those are the troughs of the wave, and that is actually how sound travels. It's just compressed air particles going through the air. Or if it's going through something else, like it could be going through the earth, like sound can travel through the earth, like in an earthquake, and then it does the same thing, but it's going through ground instead of air. So the math of sound waves, well, you're in grade 11, so you have studied sine as a function, and you've studied the graph of it, and the very basic equation of it is y equals sine x. So what you could do is I'm sure you've already done this in math class, but you could just draw yourself a graph of the sine function. And this is really meant for students who had never seen this before, but you've seen this before, so I'll skip ahead. You should know what this looks like. And that is the sine function. So this is one of your connections between math class and physics class. And I'm going to skip all this stuff. So a question you might wonder is, when it comes to physics, what does what does the y-axis on the graph actually represent? What does it mean that it's going up and down? Because sound waves don't actually go up and down, right? They go out from the source. So the sine graph does not actually physically represent the way that a sound wave looks if you were to actually somehow be able to see it. But what it does is it mathematically represents the density of air at each point along the wave. And this is an illustration of that. So this is what it actually looks like, these compressed air particles. And this is the sine graph that goes along with that, which represents the density. So these crests are higher density and the troughs are lower density. Okay, let's talk about pitch. So now we're getting into more of a musical term. So there's frequency, which we talked about last week, and then there is pitch. So compare these two graphs of sine waves. So this one has a lower frequency because basically the wave is happening less frequently, and then this one has a higher frequency. Now, what does that actually sound like music-wise? Let's go to this website, Online Tone Generator, and we can do a demo of this. So, by the way, hertz, I don't think this was mentioned before. This is the unit of frequency, and it means cycles per second. So 440 means that this wave is repeating 440 times every second, which is extremely fast, obviously. It's not really countable by humans, but and that's why it sounds like music, because it's going so fast that we can't actually hear the individual beats of it. So listen to that. That's what it sounds like. That's a fairly average musical pitch. And that is, how high or low it sounds is the pitch. Let me increase and decrease that, play around with it, and see what it sounds like. Oh, that's volume. Sorry. Let's go lower. Let's go down to, let's say, 200. And that's a lower pitch around here. go lower. How about 100? Can you still hear this? I can barely sing it, but yes, you can still hear that. What do you think is the lowest pitch you can hear? Can you hear 50? Yeah, sounds like we can hear that. How about let's try 30? If I crank the volume, yes, you can hear that. I don't know if you can hear that over the video, but try it yourself. You can go to this website and try it out yourself. Try it out yourself. 20, and I can no longer hear that. Let's try 25. It's a rumble. Like it's almost like, is it really sound that you're hearing, or is it something that you're feeling? It's kind of hard to tell. It's generally accepted that around 20 hertz is the lowest that we can possibly hear in terms of frequency. Now let's try going up higher. So we were at 440 before. Let's try 1,000. That's pretty high. That's pretty annoying. Let's try 2,000. Oh boy. Okay. I don't like that. 3,000. Yeah, still definitely can hear it. Let's go up to 7,000. Oh yeah, that's not good. 10,000. Oh boy. 15,000. Yeah, I think I can hear that. Oh, it hurts my head. Okay. I'm sure you guys could hear that. You may have heard this fact before, but generally teenagers can hear higher frequencies than older people like myself. So if we were to play a game where I kept increasing this number, at some point I wouldn't be able to hear it anymore, and you would be, because your ability to hear high frequency sounds starts to fall at around age 25. Yeah, so the range that we can hear as humans is generally between about 20 to 20,000 hertz. And that is an average range. Okay, let's go to something else here. So basically waves with lower frequency sound lower when we talk about music, and waves with a higher frequency like this one down here sound higher. So you can think about different instruments, like a violin plays in the high frequency range and a double bass plays in the low frequency range. And I'm going to skip through this part, and this part, and this part. I'll pause here to tell you an interesting fact. I remember a few years ago there was a Tim Hortons in, I believe it was Mississauga, that was annoyed that there were all these teenagers that kept loitering late at night when the store was closed. They were just hanging out outside the store. I don't know if they were like breaking things or what, or if they were just peacefully, doing teenager things. But basically the Tim Hortons decided to start playing high frequency noises at night to drive the teenagers away, because they didn't want them to hang out there, and those high frequency noises are really annoying. And so they just played it, and it wouldn't bother any adults passing by because they couldn't hear it, but it drove the teenagers away. Oh yeah, that's what I wrote down here. Anyway, so overtones. Okay, now we're really getting into some musical ideas. So let me pause and really let's try to deeply feel this concept, because it's kind of a complicated one. So when you play an instrument, and imagine an instrument that you've played before. Everybody's played an instrument, even if it's just in school, or if you play an instrument outside of school. Just picture an instrument that you've played before, and just picture playing a single note on it. Pluck a single guitar string, even singing. Just sing a single note. Obviously, I'm an amazing singer. So when you play a note on an instrument, you are playing the bass frequency. And that is what you're mostly hearing. And for example, when I'm singing, that is the bass frequency. That note that you heard is the bass frequency. But what's happening is it's also resonating, and it's also giving you other frequencies besides just the main one. In the case of singing, the resonance is happening, like inside my mouth. It's sort of an echo chamber. There's echoes kind of resonating inside my mouth and then coming out, and you're actually getting extra frequencies, not just the bass frequency. And actually, there's a mathematical relationship. those extra frequencies that are coming out of my mouth are multiples of the bass frequency. So, for example, if I play A440, which is the musical note A, which is at specifically the frequency 440 hertz, you're mostly hearing that note, but you're also hearing some of the frequency 880 because that is double 440, and you're hearing 1320, which is triple, and 1760, and so on. So you're hearing a little bit of each of these other frequencies, which are called overtones. Now, this is a really interesting concept because it helps explain why different instruments sound different even when they're playing the same note. So imagine a violin playing one note, imagine a piano playing the exact same note. It's the same note. You would think it should sound the same, right? But it doesn't exactly sound the same because it's played on a different instrument. The reason it sounds different is because you get different amounts of overtones for each instrument. And this video is just a really, really nice visualization of this concept. So let's watch this. Basically, it's going to play different instruments playing the same note, and you can see the overtones. Let's skip ahead. Oh no, that didn't skip properly. I'm very sorry. And now I'm stuck. Oh my god. Here we go. I'm just going to go to YouTube. That's better. Oops. So that word timbre, this is pronounced timbre. It is a word meaning like the quality of the sound of an instrument. You know, violin has a different timbre than piano because it sounds different even when it's playing the same note. Anyway, let's listen. Okay, let me pause and sort of explain what's going on here. So take a look over here on the keyboard. You can see which note is actually being played. It is this note, and that corresponds to this frequency, which makes sense because it's the largest. Obviously, it's the most prominent frequency that you see. But look above that. There are all these other frequencies that are simultaneously being played. So there are all these different sound waves. This is the main one, but then there's this other one up here, which is also being produced by the instrument, even though it's not the note that's being played. And they're all, look, there must be 20 or 25 different frequencies. And then when we get to the second instrument, the harpsichord, it has even more. It goes way, way up the frequency scale. It looks like we're getting up into maybe the 10,000s. So you can see that the harpsichord, because it has more high frequencies, that changes the way it sounds. And it actually sounds like a bit of a higher, sort of a tinnier, or like a colder or less warm kind of sound. So let me just go back and let's hear those two sounds again. Here's the piano. Harpsichord has more high frequencies. I don't know if you can hear that, but it's kind of cool. Now that nylon string guitar has a very warm sound. It's not very harsh. It's kind of soothing. And that's because it has a lot of low frequencies, or it doesn't have very many high frequencies. Even compared to the piano, it has fewer high frequencies. Ooh, sitar is cool. Very sharp kind of sound. Yeah, that viola is very warm. Obviously, it's being bowed instead of being just plucked at one time. So that's why the waves basically keep going instead of sort of falling away like these ones do. That's really interesting because viola and cello are very similar. They actually sound, you know, you might not be able to tell the difference between them if it didn't say which was which. So let's just listen to that again. Pay very close attention to the difference in which frequencies are more prominent for viola versus for cello. interestingly, cello, even though it's a lower instrument, it's a much bigger, cello is like you have to sit down and play it, whereas viola, you can stand and hold it and put it on your shoulder. Um, Actually, cello has a bit more high frequency than viola, but it also has a stronger low frequency than viola. So it's very similar, but there's just a couple little differences which gives it a slightly different sound. And a musical expert or a professional musician could tell you the difference between those two instruments just by listening to those two notes. That one's I find that one, the bassoon actually sounds quite a bit like a cello. And if you look at their frequencies, they look pretty similar. As a matter of fact, even though they're completely different instruments, bassoon is a wind instrument. I do not know these instruments. Now, accordion is really interesting because if you listen carefully, if you have a musical ear, you can actually hear two different notes. In most of these cases, you can't, but with accordion, one of the overtones is so strong that you can actually hear it as a distinct separate note. So listen to that carefully again. You can hear but you can also hear at the same time. And that is that. So that is the physics of why different instruments sound different, which I think is really interesting. So I hope you guys enjoyed that. Now, there's this thing called the circle of fifths, if we have time. Well, I'm just recording a video, so of course we have time. Let's do it. Now, you might be familiar with this concept if you have studied music theory. If not, no problem. So let me just introduce you to a couple of musical terms. So an octave is the interval between the bass frequency and the first overtone of a harmonic series. Now remember, for example, if the bass frequency is 230, overtones are multiples of that. So the first overtone is double. So the first overtone is 460 hertz. Now let's listen to that to see what that sounds like. So there's 440. Let me play the first overtone, which is double, 880. It sounds similar in sort of a way. If you've studied music, you know that's an octave. And those notes are both the same. They're actually called the same note. 440 is A, 880 is also A. It's not the same A because one of them is up an octave from the other one, but they're even called the same note because they sound so good together. They're not actually literally the same note in terms of physics. We know that because we have this number which measures the note. Obviously, if it has a different number, it's a different note. But just because they sound really good together, in fact, they sound so good together that we give them the same name. Okay. So what is the ratio between these two frequencies? Well, if one is double the other one, then the ratio is 2, or 2 to 1. So octaves always have a ratio of 2 to 1. Now let's talk about fifths. A fifth is the interval between the first and second overtones of a harmonic series. So here's an example. If the bass frequency is 120, that means the first overtone is 240, and the second overtone is 360. So let's go listen to what that sounds like. So what did I say? 240 is the first overtone, and here is 360. And that jump from the first note to the second note, that interval is called a fifth. We don't need to get into why. So what is the ratio between these two frequencies? In this case, it's 1.5. You can divide the numbers, 360 divided by 240, you get 1.5. Or if you put it as a fraction, it is 3 to 2. So the ratio between fifths in music is always 3 to 2 in terms of their actual frequency. So the circle of fifths. So here's the thing. If you go to a keyboard and you start playing fifths, you are eventually going to get back to your starting note after you cycle through all 12 notes on the keyboard. And if you do happen to have a keyboard, actually I can probably find one online. So let's just go online keyboard. Yeah, virtual piano. This should work. So if I start down, if it ever loads, loading, 0%. Oh, there we go. Okay, so I'm going to start down here. Wow, that really echoes a lot. I'm going to start down here at this C. If I go up a fifth, that is G right here. Then I go up another fifth to D, then up to A, then to E, then to B, F sharp. I'm going to run out of space. C sharp. What's the next one after that? I think it's A sharp. No, it's not. It's G sharp. I'm gonna have to go back to the bottom and keep going up. So G sharp goes to D sharp, which goes to A sharp, which goes to F, which goes to C, and we are back at C, which is where we started. And that is the circle of fifths. If that flew way over your head, don't worry about it. That's a real music theory kind of a thing. So, now, I meant to, let me just modify this slightly because I want to reveal it gradually for the drama. So mathematically, here's how it works. If you start with a note of, say, 100 hertz, we know that the ratio of a fifth is 3 to 2, also known as 1.5 to 1. So in order to get if you're going through the circle of fifths, you multiply by 1.5. The next frequency would be 150. If you keep doing that, well, you just keep multiplying by 1.5, and then we're going to do that 12 times. And because there are 12 notes in the scale, the last one should get us to a note which is the same note as the note that we started at. And we started at 100 hertz. And if we double 100, we get 200, 400, 800, 1600, 3200, 6400, and then 12,800. And we ended up at a note which is a number which is pretty close to that. It's not, but here's the thing, it's not exact. It's not perfect. It ends up pretty close, but not exactly. So actually, there's a bit of a math error in the musical scale, which is a whole other thing that we don't need to get into right now. But music is founded on mathematics, but with a little bit of a mistake. We don't need to do that. Oh, I forgot this is a little video that I made a few years ago, which is a song based on the Fibonacci sequence, and it also demonstrates how the Fibonacci sequence gives you the shape of a spiral galaxy, which is kind of cool. You can watch that on your own if you like. And that's it. Anyway, I hope you enjoy. I know that was a bit long, but the physics of music is really interesting. There's lots more to it than just what I talked about. I hope you enjoyed that. And yeah, that's it. Thanks for watching, if you made it this far.